Okay. Hello everyone, welcome to recitation number 11, and today we're going to be continuing some undecidable problems and more reducible problems, even though like the two ideas are related to each other. Usually if you're solving one, you're essentially solving the other. Okay, so last time we talked about the decision problem, which asked this question: is there an algorithm that takes as input a statement written in formal logic and produces a yes or no answer that's always accurate, like mean it's always correct. We don't just want an algorithm that's going to answer yes or no randomly. We want that answer to be correct, to be about like a formula where we're checking if there's a number that's bigger than or numbers, like is there some n0 such that for every n that's maybe not n0, that number is going to be bigger than all of them. And obviously the answer for that is going to be no, but we would like to know if there's an algorithm that can solve harder problems. So we don't have to like run our program and keep waiting and waiting. But in other words, other than seeing it in this format, we could have asked it like this: is there an algorithm that can determine, given the description of a Turing machine and the input of its tape, whether this machine will run forever or halt? Sort of like the same scenario, like you're running your program. Will this program ever stop running? Like, will it halt? Will it stop? Will it terminate? Or is it going to run forever? That would be useful to know. But the answer for that is no. And we proved it using contradiction. And with contradiction, we start off by assuming the thing we're trying to prove is not true. We assume that it is true. So assume that such an algorithm does exist, and we called it H. And this is the question that we're asking. Is there some H? You give it a program. You give it the input from its tape. So that program, like it could be the description of a Turing machine itself. And this H will be able to correctly tell you yes or no whether this program halts on this input. So that was our assumption. This is something that now exists. We're assuming it's true. And we build on top of it, just like with EQDFA, with EDFA, all of those previous decidable problems where we assume they're true and then we use them to build something bigger. We're doing the same thing here. H is now simply a part of a bigger machine that we're building. And this machine takes one input that will be split to both entries of H. And we made certain wirings like, oh, if H says yes, we'll loop forever. If H says no, we'll say yes. There's a reason for that. And the reason is now what happens when I feed C itself. Okay, so what happens when the machine C takes as input itself C? And again, not really hard to imagine it. Just imagine you wrote a program in Java or whatever, and it takes an input string. You're giving the whole description of the program into itself. It's not the same thing, but just like for imagination. So what happens when C takes itself as input? Well, this gets split into both ways. So you're literally asking H, what does C do when it takes itself as input? And that's literally what's happening outside. We have a machine C that's taking itself as input. And inside, you're asking H, what does C do when it takes itself as input? Now, remember that H is a machine that will be able to correctly tell you whether C will halt on C, or like will any machine halt on any input, no matter what. We're just being specific with, oh, C takes itself as input. So will H be able to predict correctly? Well, there are two scenarios. Either H will say yes or no. If H says yes, C will halt on C. C actually loops forever. That's how we made it. This C is being fed itself, and it's looping forever. So in this prediction, H was wrong because it said yes, C is going to halt, but it actually loops forever. Well, what about the other scenario? If H says no, C will not halt on itself as input. C outputs yes, and it stops. Like whenever you output accepting or rejecting, that's like you halted, you stopped. So C actually just accepts, and so in other words, it halts. So in both predictions, H was wrong in predicting what C is going to do when it takes itself as input. And really, because of that, H can't exist. We assume that H is a machine that will be able to correctly always tell you whether a program will halt or not. But here we found a machine that it predicted wrong, so it doesn't exist. Okay, and after that, we solved this problem on loop TM. So right now, just giving you like a short summary of what we did last time. Now with loop TM, what is it? It's the language where you take a machine M, where W is a string, and M loops on W. So what is the computational problem here represented by loop TM? It's literally like the description. Is there a machine So if this language is decidable, that means there's a machine. You give it M, you give it W. It'll be able to correctly tell you yes if M loops on W or no. We want to prove that such a machine doesn't exist, like this language is undecidable. And really, the intuition here is we try to relate it with ATM. What's ATM? It's the language such that it takes as input M and W, and to be able to correctly tell us if M accepts W or not. This language we know is not decidable. We actually even proved it last time with another problem using similar logic, using similar idea to what we did with the halting problem. So we know that ATM is undecidable. Why? Well, really, if we wanted to make a machine that will do this, we're gonna just simply run M on W. Like really, to know if M accepts W, there's nothing you could do other than run M on W, because M is the only machine that's gonna know if it's gonna accept W or not. But when you do that, 3 scenarios. Either M accepts, M rejects, and these aren't a problem, but the third scenario is the problem, which is what if M loops on W? That's the main issue. That's the problem. What happens if M loops on W? We don't know. Like you never know should I reject, because it might be it might end sometime soon. You can never know if something is just looping forever or is it just taking a long time to terminate. So this is the problem that makes ATM undecidable. However, now in this question, we're assuming there's a machine, call it for example R, decides looptm. So looptm is the language, R is the actual machine that decides the language. We're saying, oh, there's an R that will be able to correctly tell you whether a machine loops on its input or not. If such a machine existed, well, it solves this third problem that makes ATM undecidable. Does M loop on W or not? Oh, you have a machine that does that. So before you run M on W, like if we're trying to build a machine, say X, that decides ATM, before we actually run M on W, we'll simply check, does M loop on W using this machine? If it says yes, we'll reject right away. Because if it's looping forever, it's not going to accept, we simply reject. Otherwise, if it says no, it's not going to loop on M and W, well, now we can safely run M on W. If M accept, accept. If M rejects, reject. And essentially what we did, if we assume that looptm is decidable and we have this machine, we were able to create a decider for this. And that's where we get a contradiction. We know that ATM is undecidable. And essentially, this is the theorem that we used. If you have some language that you know is decidable, and you're able to reduce another language to it, then that other language must be decidable. So we assumed that looptm is decidable, and we were able to use it to build another machine, which is ATM, that we know is undecidable, but the theorem tells you now that ATM is going to be decidable, so that's a contradiction. It is known that ATM is undecidable, but you prove that it is, yada, 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 it's wrong. Okay, so that's a quick recap of everything we did last time. Hopefully, if there's a part of this that you don't get, let me know. Because we're going to be continuing with this notion where we assume that something is decidable, something that we want to prove that's undecidable, like this next part. We want to prove the following language is undecidable. So actually, let's read it a bit first. So what's going on here? The language ABB. It takes as input M. M is a Turing machine, and M accepts AB. What is the computational problem that is represented by this language? Any idea? Because it is actually important. It might be confusing. They're not saying you want to create a machine that accepts ABB. That's easy to do. You can simply make a DFA that accepts ABB. So obviously you can make a Turing machine. That's not what they're saying. They're saying, can you create a machine that takes as input another Turing machine? Like for example, this one, I'll call it maybe R. It takes an input another Turing machine, and it'll be able to tell you yes if M accepts A, B, B, and no otherwise. Call and a string, and it checks if it accepts it or not. A string, exactly. And you're asking the acceptance problem. Like, what do you mean by that? Like, can I relate it to ATM like before? Am I lagging? Test. Okay. Let me try something. Okay. So as we were saying, yeah, it might have to do with the acceptance problem. Like there's an issue here. So assuming that this, it seems like a silly problem, right? Like, oh, is there a machine that will be able to correctly tell you whether another machine accepts the string ABB? If such a machine exists, it's gonna cause problems for other stuff. Like if this machine exists, yes, we'll be able to create a decider for ATM. So just like before, if looptm existed, we were able to solve, we were able to make a decider for ATM. Same thing here. If this machine exists, we'll also be able to make a decider for ATM, even though it might not be as obvious because before, oh, looptm solves the loop problem. But here too, ABB solves the loop problem. We just have to create it in a certain format. So this is what we're going to be doing. So just try to understand it with me. And the next the next exercise is actually pretty similar. So go with me on the construction here, and later you can try it yourself. So I'm going to do the following. So remember, at the end goal, Jad, so because ATM can be reduced to ABB and then ABB must not be decidable, exactly. We're assuming that it is. So step one is always assume ABB is decidable. And if it is, we get this machine. So we get a machine that decides it. And now we're going to use this machine to make another decider for ATM. And by doing so, by making a decider for ATM, that's that you just reduced it. You reduced ATM to ABB, which makes it decidable, but we know that it is undecidable. Okay, so how can we do that? So it starts as this. Remember, the whole point is to make a decider for ATM. So I'm going to make like a big machine that takes M and W. And ATM should tell you correctly whether M accepts W or not. Okay. So now what are we going to be doing inside? Obviously, we want to use R, but there's something we have to do before that. I'm actually going to build another Turing machine. I'm going to call it M prime. And M prime takes as input, say, W prime. So it's a completely different machine and different input than what we have outside. We're creating this ourselves. Let me actually make it slightly bigger. So how am I going to create this machine? As follows. If W prime is not ABB, I'm going to reject. Why am I rejecting? Just go with me. Say if M prime gets any input, so this is the name of the machine, M prime, gets any input that's not ABB, it's going to reject. Because we care about ABB. However, if it is, so otherwise, if W prime is ABB, when am I going to accept? Well, I'll run M on W, and I'll accept if M accepts W. Does it make sense? M prime, it's taking as input W prime. If that W prime happens to be ABB, I'm not going to accept right away, nor am I going to reject. I'm simply going to run M on W, M being the input that ATM is taking, and W as well. I'll run M on W, and I'll accept if M accepts W. What can we really deduce from what I wrote here? We can deduce the following idea, that M prime is going to accept ABB if and only if M accepts W. Makes sense, right? We constructed W prime in that format. It's only going to accept ABB if and only if M accepts W. Okay, now we come to the other step. So if this was like step 1, where we created M prime, now we go to step 2. Now we use this decider R. Remember R, you give it a machine, it'll be able to tell you yes or no correctly if that machine accepts ABB. So now let's run R on input M prime. R is either going to say yes or no. So let's see. If R accepts, what does that mean? R accepting, remember R is you give it a machine, it'll tell you yes or no if it accepts ABB. If R accepts for some reason, this must mean that M prime accepts ABB. But with what I wrote here in the green, if M prime accepts ABB, this is as if M accepted W. Do you see that? The construction. So we can actually plug this right in here because we made it in that way. Oh, if your input is ABB, just run M and W and accept if M accepts W. So if by R saying yes, this machine does accept ABB, we can conclude that M accepts W. Otherwise, if not, if R rejects, that must mean that M prime, or sorry, M prime rejects ABB, or doesn't accept ABB in other words. But when does this happen? Two ways. Either M rejected W, so let me plug in this right here. Either M rejected W, or maybe M looped on W. So you can see here, it also solves the looping problem. Because if M prime rejected ABB, what does that mean? You ran M on W, and M never accepted W. If it did, we would have accepted ABB. But it didn't, so it either rejected it or it looped forever. Remember, R will correctly tell you if the machine will accept ABB. So if M prime ever accepted ABB, it must have meant that M halted on W, and it either accepted. So we can plug this in right here. We're gonna write it formally, but is there any problem with like the drawing that I did? First, I constructed this machine M prime. Like usually we're accustomed maybe before to create a DFA or to create an NFA. We never created another Turing machine inside. Jad, so we're using using prime, we can decide ATM. Yes. Before we just used so in the exercise before we just used looptm right away to solve our problem. Here we couldn't use R right away. Remember, R decides ABB. We couldn't use it right away. We had to first create M prime that using its manipulation, yes, it'll let us decide ATM. Okay, so let that maybe bobble in your head as we'll give an official description for it. Okay. Again, if there's a part that confused you, let me know. Let me just temporarily see what do we want to clean that. So X takes as an input M and W. Where M is a Turing machine and W is a string. What's the first thing this is going to do? Or inside of it, we created M prime as followed. On input. So like this is another machine inside our original. This one takes an input W prime, where W prime is a string. It's checking. If W prime is not equal to ABB, it rejects. If W prime is ABB, well, that's where like the manipulation happens. You'll accept if, so run on W. What is this M? What is this W? It's the original input of X. Run M on W, so they do exist. They're not, they are arbitrary, but they do exist. And we'll accept and accept if M accepts W. That's ATM. Okay. Can you go over here? Okay, so we created M prime. Now we go to step 2. Let's actually run Turing machine R on input M prime. Knowing that R decides ABB. What's going to happen? If R accepts, this tells us that, oh, M prime accepts ABB. So like it's almost like I'm literally just the things that we drew here, I'm just repeating them. So M prime accepts ABB, but that means that M accepts W. So we should accept. When I say right here accept, I'm talking about the machine X. It took input M and W, and it's saying yes, M does accept. Why? Because of this sequence that happened before. Now, if R rejects, what does that mean? Well, M prime doesn't accept ABB, which means M doesn't accept W. And this could mean two things. It could mean either M rejected W, or M loops W. We do this part, like this is the part that makes it, that made it the original language undecidable. Either way, we don't care. We're just right away gonna reject. So X is rejecting, which means, oh, M doesn't accept W. And yeah, essentially this is it. So I'd say, yeah, the hard part maybe is what we wrote here, like creating a machine on the side that we'll use in Cohere and we'll use with our design. But any major problem is, are you lost anywhere here? Okay. Now, just a few remarks. I know here that I'm saying, Jad, what's the difference between R and M? Okay, very important. M is any Turing machine that's X is taking. What and X is going to be a decider for ATM. You're right. Like there's a lot of letters, we can get confused. M is simply any machine that ATM is taking as input, and we're checking if M is accepting W or not. However, R not the language Ghafran. R is also a Turing machine, but it decides the language AAB. So R is a decider for the language ABB, meaning it'll be able to correctly tell us whether M prime, so it's taking M prime as input, it'll be able to correctly tell us whether M prime accepts ABB or not. Specifically here M prime, but it could be anything. Like we already originally we described it as any. Okay. Mhm. Okay. Let me know if that's good, chat. Now a few remarks. Here I know that I'm saying if W. I'm saying here if W prime is not ABB, reject. Actually, here it doesn't matter. You could have said reject or you could have said accept. I don't think it makes a difference because think about it. If W prime is anything other than ABB, it doesn't matter if you accept it or reject it. What we care about is if it is ABB, whether you accept it or not. And the way that we made it, oh, we're gonna accept M accepts W. Okay. So in short, at the end, oh, X decides ATM, but we know that ATM is not decidable, so contradiction. Since ATM is undecidable. Okay. Now, let's move on to the next problem. If you didn't completely get this, maybe the next one, which is essentially we're just going to be repeating ourselves. So here, another language. It takes as input this time two machines, M1 and M2, and it's checking if the intersection is empty. So this language is actually undecidable. So we'll try to do this together. The problem, what's the computational problem here is the following. Oh, I have a machine M1. I have a machine M2. Obviously, they're Turing machines. And I will say yes if their languages are the same, or sorry, if the intersection of their language is nothing. And no otherwise. Hmm. Why is this a problem? Hint, we're going to try to relate this with Halt TM. And it does. We could actually hold it with ATM. Even the problems, or I know TM. You, what's Halt TM? Machine takes M, takes W. It'll tell you yes, or it'll accept if M halts on W. You can see why they are really like why you could have if you're using ATM, it's the same as if you're using HaltTM because HaltTM tells you that M halts on W. If you know that it halts on W, it's as if you will know if it's going to accept or reject. Because really, the problem with both machines is whether we're going to loop forever or not. Jad, we don't know if M1 or M2 halt or not. That's the problem. Mm, yeah, you can think of it like that. The actual problem, more specifically, is that we don't know if M is going to hold on W. But we're gonna be using this R. So again, I'm going to call it R, which decides the language D. We're going to be using this machine with some more construction to figure out if M holds on W or not. Okay. So we're gonna be actually needing to create two machines here. So this takes as input two machines, M1 and M2. We're gonna create two of them. Now, how can we do that? Well, let's worry about the first machine. So I'll create M1. So our Turing machine takes any arbitrary M1 and M2. Here, I'm just like specifically specifying some M1. You could name it whatever you want. And this machine takes, say, some input W1. Now, what do you want to do here? And we're going to be creating later another machine M2. It takes as input W2. And both of these, we're going to be feeding them into R, and R is going to tell us whether they're the same language or not. But how does that really help us with the halting issue? Okay, I'm not going to create anything new. Let's give it the same description as before. How about that? M1, I'm simply going to make it the same thing as the previous problem. So I'll make, oh, if W1 is not ABB, I'll reject or accept. Remember, this doesn't matter, but you have to choose one, either accepting or rejecting. If W1 is ABB, you guessed it, I'm simply gonna run M on W, and I'll accept if M halts on W. So instead of before, oh, I'll accept if it accepts, this time I'm accepting if it halts on W. So what can we deduce from this one, like before? The language of M1 is going to be ABB. This time it might be actually important to reject here. So the language of M1 is only going to be ABB if and only if M halts on W. And actually, what do you think the language is going to be for M1 if I don't halt on W? Exactly, chat. It's just going to be empty. Like, I'll only accept ABB if M halts, and if M doesn't halt, oh, my language is nothing. My language is nothing. So this kind of relates to the original problem. I'll be checking if the intersection is empty or not. Any idea what kind of description I could give for M2? Like, I want something here. Whoops. Like the end goal, I want a similar conclusion where I check if, oh, if M2 is going to be something, if M halts, and it's going to be something else if it doesn't halt. If doesn't. Mhm. How about this? I'm feeling lazy. Let's just give it the same description. Let's just give it the same description. Nothing stopping us. Oh, here's same thing. If W1 is not ABB, or I'll call it W2 actually, but again, it's all arbitrary. So M2 is taking input W2. So if W2 is not ABB, we'll reject. Otherwise, if it is, I'll only accept when I run M on W and M holds. So the same description as before. which means it's the same conclusion. So same thing here, like L2's the language is going to be ABB if M holds, and it's going to be nothing if it doesn't hold. What could I deduce about the intersection now? If the intersection between both of them is empty, what does that? Exactly, as Jad is saying. If the intersection is empty, well, it's the same thing for both. If the intersection is empty, that means both of them have to be empty. So that means I think Jad, what you meant is doesn't hold, right? Doesn't hold if the intersection has to be happens to be empty. If it but what is the other scenario for the intersection? So what would the intersection be if M does hold? Exactly. If that does hold, well, they both of them they simply accept ABB. So this is if M does hold. So far, I haven't used R yet. So far, everything that I've done is construction, and just to make it like easier, we used the same from the previous double B. Otherwise, M and W, and we got all of them. What happens if I run R on M1 and M2, the ones that I actually created? So if these two, we put them as input here. And R says yes. The intersection is empty. Well, we did use this, that M does halt. Remember W, the original input on W. And here, oh, sorry, M doesn't halt. And here it does halt. Did I lose you? So we constructed M1 and M2, and they're the same machine. Both of them, they're the same. They're only going to accept ABB. They're only going to accept ABB if M halts on W. Well, if I now put both of them in my decider R, and R intersection between both of them is M, that could only mean that M doesn't halt on W. Because if it did, they would have gotten, because if M did halt on W, they would have both accepted ABB. And yeah. So we're gonna now, just like before, I'm gonna give the formula, for so wanna with a am I lagging? I feel I might be lagging. Let me know if you can hear me. Okay, so M and W, where M is a Turing machine, W is a string. Okay, great. Step one, M1 as follows on input. W1, and you can really call these whatever you want. It's just letters. So this machine that's on input W1, where W1 is a string, we're doing the following. If W1 is not ABB, reject. This time it's actually important that I reject because actually I'm not sure if I would have put this except, what do you think changed? If I had put this when W1 or W, not ABB, if I would have accepted, well, actually oh, sorry, on W. Let me actually. So Fran, can I repeat what happens if we put it except? Sure thing. Let me actually do it here. The, what accepted? Like they have to be same machine, so like the intersection is always equivalent. So if you decide to put reject or accept, it has to be the same on both. Well, if I put accept, what's going to be the language of M when it does halt on W? It's going to accept ABB, but it's also going to accept everything that's not ABB. So here it's going to be sigma star, like everything. But if it doesn't hold, that means it didn't accept ABB. Well, now it's going to be everything. So sigma star minus ABB. Like whatever you can create strings except ABB got rejected. And same down. But that means section is what? The star and your feet of the the and we well T T. This is why so now if W we run them on W and accept if M halts on W. Now we create M2, same thing like M1. Like it takes a different input, even though like we could have also named it W1. It doesn't really matter. Like imagine instead of W1, had I said something like just Y for everything. Doesn't really matter. Okay, now comes part 3. Or first of all, let's say notice if the intersection. So if the language of M1 intersection with M2 is empty, that must mean that R doesn't halt, or sorry, M doesn't halt on W. Otherwise, if it is, so if it's just like ABB, that means M must have halted on W. And like this is the magic. We were able to answer the question whether M halts on W or not, which is, remember, the whole point of the halting problem. So now we can safely say run R on input M1, M2, such that R decides, what was it named? I think I lost that. Oh, I think it's right here. It's just named D. So R decides D and D does that whole thing. And we'll accept if the following happens. So if R accepts, that must mean the following. So we accept. Sorry, we reject. So here actually the wiring is opposite. Our accepting means the intersection is opposite. So it means the intersection is empty. Means M doesn't hold, so we should actually reject. So originally H doesn't hold. Other way around. If R rejects, so we get the other conclusion. So we should accept. Okay. Any problem here? I'm not telling you it's like easy to swallow the first time. It's a tough pill, but it's kind of there. Now, important remark, why did I say ABB? Well, I said ABB just because the previous problem had that, so like it might be easier to relate. But really, this specific string, it could have been anything. Like say I just decided to use the M's, I did everything else. Let me replace epsilon everywhere, and what happens? So if the intersection is empty, M doesn't hold. If the intersection is the empty string instead of ABB, it must have halted, and yeah. The only thing that changes is instead of ABB, you get like the empty string. So just choose something specific, and that's what you get. All right. Let's do one more, and we'll see what energy we have. So we're gonna be doing something different now. There's actually gonna be a proof that's given to us, and we're gonna try to read it. But before that, let's try to think of maybe a proof ourselves. So in this question, let H1 take the Turing machine M as input. M is a Turing machine, and M halts on M. So what is this question asking? If it is sorry, they're not asking about decidability here. They're asking about this. Is the complement of H1 Turing recognizable or not? Now they're saying to prove that it's not Turing recognizable. So that means H1, the complement, is not Turing recognizable. Like you can't have a machine where it takes as input M, and it'll tell you yes. So it's called M. Oh, sorry. The machine can be called anything, but as usual, we call it R, and R is like a recognizer, so not a decider, very important. It's a recognizer for H1 complement, meaning If R takes as input M, it'll tell us yes. If M halts on, or doesn't halt, my bad. So the complement of H1, it'll check if it doesn't halt, since H does check, H1 does check. So if it doesn't halt on M. Jad, if a language and its complement are both recognizable, then the language is decidable. Exactly. So what Jad is saying, if we can prove that H1 is recognizable and H1 complement is recognizable too, that must mean that H1 is decidable. And that's actually, we're going to be doing that in the next part. But in this part, they're asking to prove the following, that H1 is not recognizable. So that definitely must mean that H1 is not decidable, because they're telling us to prove that a part of it is not recognizable. This is similar to ATM, right? Like ATM is recognizable, but the complement is not. The complement is when should I reject? It has the problem with the looping, so it's not recognizable. So that's why the whole thing is not decidable. But back to this problem. I take M as input, and I should be able to tell you yes if it doesn't halt on M. Hmm. Okay. I'll actually leave it to you to try and maybe do something similar to what we did before with this problem, because there's something there. What we're going to be doing is check a solution that's given to us, because there's another way of thinking about it. But is there any issue with the question, what they're trying to say? We're checking, is there a recognizer for H1 complement? H1 complement says, oh, M doesn't halt on M. So on itself as input, not on some random input. Okay, let's see how they did it. First, they said the complement is as follows. It takes M prime. M prime is either not M or it is, but M doesn't halt. Let's just focus on this part. This is what I care about. The complement of H1 means M doesn't halt on M because the original one, it did halt. So hopefully we all agree on that. Carla, we can inverse the accept and reject states. Oh, Carla, that would only, so Carla's saying actually something very important. Let me write that as a remark. Can we inverse the accept and reject states? This is a theorem. So I think we actually solved this in a previous recitation. This is from a theorem that's as follows. If L is decidable, then L complement is decidable too. It's not just inversing the accept and reject. So if you remember, we actually did something on top of that, but it's essentially it's kind of that, like inversing these on top of other things. But remember, the theorem assumes this: if M is decidable, then the complement is decidable as well, so we can flip them. But here we don't have that. Here we don't have that H1 is decidable. All we know about H1 is we don't even know if it is recognizable. They're just trying to tell us to prove that the complement is not. So we can't really use this theorem. So we can't use it here because we don't know anything about the language H, whether it is decidable or not. And since they're actually saying to prove that H complement is not Turing recognizable, that must mean that the language is not decidable. I say probably, but like it's definitely. Okay, where were we? And again, just like a quick remark, remember, if L is decidable, Jad told us that, oh, if L and L complement are recognizable, then L is decidable, like this one here. If H1 and H1 complement are recognizable, then H1 is decidable. The inverse is also true. Like if you have H1 is decidable, that must mean the other two parts are recognizable. And this is why here we can't do the inverse. But Ajad, if we prove that H is not decidable, then we prove that its complement is not recognizable. That's also one cool way of doing it. That's one cool way of doing it. If you can prove that H is not decidable, but you have to prove that H1 is also recognizable. So you have to prove two things. You have to prove that H1 is recognizable, and you have to prove that H1 is not decidable. Using these two, you can prove that H1 complement is not recognizable. Because if it was, it should have been the H1 should have been decidable. And that's actually what I want you to try to do on your own time. Because the first part is easy, recognizable for H1. Like M halts on M, you just run it. And if it does halt, you accept. That's for the recognizable. For the not decidable, you might want to do something similar to what we did before. But here I want us to see a new idea. So, okay. So H1 complement, simply M doesn't halt on W. So they're actually trying to prove the following. Imagine it like this. You have the set, which is H1, and everything outside is H1 complement. What they're actually going to prove is the following. So they said let S be the recognizer for this machine. And they're going to try to prove that S doesn't belong in H1 and S doesn't belong in H1 complement. Makes sense, right? Like if a machine, we're assuming that S is a machine and it recognizes this language. But if it doesn't belong in H1 and it doesn't belong in H1 complement, then it can't be in our universe because these two sets give you all the Turing machines like ever. Okay, so case one, they're gonna suppose that it's in the complement. What does that tell me? S doesn't halt on S. If S belongs to H1 complement, it must mean that S doesn't halt on S. However, S is a recognizer for H1C. So remember, S is a machine. You give it some machine M, it'll be able to tell you yes if M does not halt on itself. This is something that we've already assumed. But when you say that S is in the complement, you're saying that S doesn't halt on S. This is what you get when you say S belongs to the H1 complement, because H1 complement is simply those. If there's a machine inside of it, that means it doesn't halt on itself. But when you add the fact that S is a recognizer, what does that mean? Whatever machine you give S, it'll be able to correctly tell you if it halts. Sorry, if it doesn't halt. Like if you give it anything, any M, it'll be able to tell you if M doesn't halt. Including S. If I give it S, it should be able to tell me yes, S doesn't halt on S because it's a recognizer for it. It should be able to, and S does belong to my set, should be correctly to, should be able to tell me that. But if this happens, that must mean that S halts on S. Do you see it, or is it confusing? First step is when you say it belongs to the language H1 complement, it must mean that it doesn't halt, because that's what the language is. Second thing is, we assume that it is a recognizer for that language. So if I give it S as itself, and knowing that S should not halt because of step 1, this machine should tell me yes. Yes, it doesn't halt. But there's a contradiction here, like it's trying to say that it doesn't halt on itself. But in order to say that, it should halt. So let me type it out. Maybe it'll be better to get. So first of all, we said that OS doesn't halt on S, but S is a recognizer for the complement. So if S takes itself as input, it should be able to tell me that S doesn't halt on S. It should be able to tell me that because it's a recognizer, like you're assuming that it doesn't halt on itself. So if you give it itself as input, it should be able to tell you that. But in order to do that, it should halt, which is the contradiction. But to do that, it has to halt, which is a contradiction. Exactly, Jad. There's two ways you can get a contradiction here. If it actually doesn't halt on itself, it's no longer a recognizer, because it should be able to tell you yes. Otherwise, if it does halt, that's a contradiction with the original one. So no matter how you spin it, there's a contradiction here with the first case. Let's try the other case now. Suppose S is not in H1 complement. That must mean it is in H1. If it is in H1, we get the following information. M halts on itself, so S should halt on itself. So this is what we're getting from this first point. However, can you tell me what they're doing here? So they're saying that S is a recognizer. If I try to give it itself, it's not going to say yes. It's not going to say yes because we just said that it should halt on itself. So what do then they say? Since S is a recognizer, meaning it doesn't know if it should say no, then that means S should halt on itself. Do you agree? So I'll draw it one more time. S takes some machines as input. It'll say three things, right? It's either going to say yes, it doesn't halt on itself. It's going to say no, it does halt, or it doesn't know. Like so there's a problem that it might loop on itself. When I give it the specific input S, we know it's not going to say yes. Because of step 1, we know it will halt on itself. But now what they're saying is it's definitely gonna say it's definitely gonna not halt on itself. Does that make sense? Or is there something wrong here? I don't think this proof is correct actually. Why? Okay, there are three scenarios. Either it says yes, it doesn't halt on itself, Or it says no, so which means it does halt. Or step 3, where it's a recognizer, where it since it's a recognizer, there's a chance it might loop forever. What they're saying is, because of part 1, they're assuming that, oh, it must halt, so definitely yes will not happen. Because of step 1, it's assuming that it does. But then they're saying, oh, it's a recognizer, so it shouldn't halt on S. So it must definitely loop forever. And I don't agree with that. Because there's the chance where it might simply say no. It does halt on itself. So yeah, there's actually something wrong with this proof. And it's right here. Let me repeat it one more time and you can tell me if you agree or not. Like they're assuming something that they shouldn't. S is a recognizer. So 3 scenarios. Either it says yes, or it says no, or it might loop forever. Using the first assumption, oh, S doesn't belong to the complement, so it must belong to the original state. Using this, we know that S is gonna halt on itself. So we know this information. S should halt on itself. So we don't get the yes, because here the yes means it doesn't halt. Remember, S is a recognizer for the complement. Okay. But now they're saying, since it doesn't belong to the complement, meaning it doesn't say yes. So the same thing, it doesn't say yes. Since S is a recognizer, it shouldn't halt on S. And this is my problem. They're assuming since S doesn't say yes, that it's definitely not gonna halt on itself as input. But no, there are 2 scenarios. Either it says no, or it loops forever. They're assuming this part. They're assuming since S isn't gonna say yes, that it's definitely gonna loop forever. But there's a chance that it says no. Exactly, as Jad is saying, the recognizer can still say no. And let's actually emphasize on this. What does it mean when I say no? It's as if I'm saying it doesn't halt, so S, or M, halts on M. There's a chance that it might say no, M does halt on M. And this is actually our assumption that S should halt on S. So it's actually definitely gonna say no, since we assume that because of step 1, S should halt on S. So yeah, there's a problem here with the solution is, so we have to be careful with that. Here they're assuming this part, like it's definitely gonna loop. Jad, the recognizer can still say no, but they're assuming that it doesn't. Exactly. They're only assuming that it's either gonna say yes or it's gonna loop forever. Maybe that's how they describe it. Like the recognizers might have different definitions, but actually I'm pretty sure here that like it's global. A recognizer is gonna say yes correctly. It might say no, or it might loop forever. You can't always assume it's gonna loop forever, right? So yeah, that's the problem here. And just a little side note, I actually don't even agree with this description here. You remember when I drew the complement, right? Imagine this is literally the universe of everything. That confused me too, Jad. This is the universe of everything. So if H is here, and H1, and H complement is outside, H1 is what? Where M halts on M. So H complement, which is everything else, is where M doesn't halt on M, or where M might not even be a Turing machine. So here I think they messed up the description. So the H complement is either where M doesn't halt on itself, Or where maybe even M isn't a Turing machine, like it's you didn't correctly give the description of a Turing machine. So like it's literally everything else. But we focus on this part, the part of doesn't halting, because that's what causes the problems. Okay. Right. Mm, I think we're actually gonna stop here because we've been going for a little while. Mm. So let's do a quick recap, maybe. So there are still a lot of interesting questions that I want to solve, so maybe we'll solve them next time. So this part, try to think about it. Show that if a language L and its complement are Turing recognizable, then it is decidable. This is what Jad said a while ago. If L is Turing recognizable, or like just recognizable, and its complement is recognizable as well, that must mean it is decidable. So you have to try to do maybe a description like I did before, where O and on input, etc. Any maybe intuition on what might we do here? So if L is decidable, what does that mean? If W belongs to L, or sorry, if there's a machine, you're giving a W, you should be able to tell me correctly if W is in L or if it's not in. Give it some W. It'll tell you yes if W belongs to L, and that's it. And you have L prime, which is if it also takes some W, it'll be able to tell you yes if W belongs to the complement. Or in other words, if W doesn't belong to L. So like you have these pieces and puzzles, you can build a bigger one. Okay, let me see what Jad is saying. If you can recognize the correct inputs and you can recognize the incorrect inputs, then you can always determine whether it belongs or not. Exactly. So since L is Turing recognizable, you can recognize the correct ones. Since L complement is Turing recognizable, you can recognize the incorrect ones. Like the correct ones for the complement. And the two machines. Do one step for Testing 1, 2, 3. How about now? Essentially, what I was saying now is just like if you have any questions, we're going to be trying to solve the two machines, like the Turing recognizable for L and L complement. You're either going to be using sequential or parallel. If you do sequential, it's going to cause problems. Parallel is going to work, but you have to figure out, well, how can I run them in parallel? Okay. And that will lead to the other questions, which I'll leave available for you to think. And next time we'll talk in detail about the mapping reducibility. Because so far, for mapping reducible, we're only saying, oh, I use a machine to build another machine. But there's really like definitions for it and meanings to it, which we'll see next time. But if you had a problem on any of the previous questions or any question in general, let me know now. Otherwise, I'll see you next time. Okay. Okay. See you on Tuesday, I guess. Anytime, Shad. Bye bye.